Have you ever wondered, what if I could just time travel and do something better? Or just time travel to see what's going to happen in future? All of us have thought about that at some point in our lives, but is that really possible? Well, it is, and science has proven it, but not in a way you might have imagined it. Is time travel possible? Well, the short answer is yes, and you're doing it right now, hurtling into the future at the impressive rate of 1 second per second. You're pretty much always moving through time at the same speed, whether you're watching your favorite Netflix show, sleeping, or thinking about inventing a time machine. But that isn't the kind of time travel we think about, and certainly isn't the kind of time travel that captivated countless science fiction writers or spurred a genre so extensive that Wikipedia lists over 400 titles in the category movies about time travel. Although many people are fascinated by the idea of changing the past or seeing the future before it's due, no person has ever demonstrated the kind of back and forth time travel seen in science fiction, or proposed a method of sending a person through significant periods of time that wouldn't destroy them on the way. As physicist Stephen Hawking pointed out in his book Black Holes and Baby Universes, the best evidence we have that time travel is not possible is that we have not yet been invaded by hordes of tourists from the future. Science does support some amount of time bending, though. For example, physicist Albert Einstein's theory of special relativity proposes that time is an illusion that moves relative to an observer. An observer traveling near the speed of light will experience time with all its after effects much more slowly than an observer at rest. Let's explain that a little bit. You see, Albert Einstein said that everything we measure it in relation to something else. For example, how would you know that something is big or small? Well, you measure it in relation to something else and then see if the thing we measure is bigger or smaller. Also, Einstein's theory says that speed of light is constant no matter what and nothing can move faster than light. From all of that, we can derive that an observer traveling at high velocity will experience time at a slower rate than an observer who isn't speeding through space. Best way to explain it would be to imagine standing still with your friend by the road and watching a car go by. Let's say that the car is moving at 20 miles per hour. If you're standing still, you're seeing the car moving at 20 miles per hour, right? Okay, now let's say that you start running in the same direction the car is going at 10 miles per hour. In that case, for you, that car would appear to be moving slower, right? How much slower? Well, exactly 10 miles per hour slower. So for you, the car would appear to be moving at only 10 miles per hour. But for your friend that is still standing still at the starting point, the car would still appear to be moving at 20 miles per hour. And he would be thinking, what the hell are you doing? So if we now imagine that a car you're following is actually time, we can say that time is moving slower for you, who is moving, than for your friend that is standing still. Of course, the numbers are different, but you get the idea how it works. Well, maybe my idea of explaining it is not practical. Here's how an English physicist Brian Cox would explain it.
Actually do it because it would require a great scientific effort and a lot of money, but no one would ever be able to prove
we do it.
that they'd been in the future.
It's been proved. So moving clocks run slow.
Has it been proved?
Yes, moving clocks run slow relative to stationary ones. So if you were to run across this studio now and run back and sit down, and we measured the time on your watch very accurately, it would your watch relative to mine would have run slower. And that's actually central to the way the satellite navigation system works. I know a number, which is the speed the protons go around the Large Hadron Collider. Mm-hmm. So they go around the Large Hadron Collider at 99.99999% the speed of light. At that speed, time passes 7,000 times more slowly for the protons than it does for the experimenters sat watching them going around, and that's relativity. So every time someone gets on a rocket and goes to the moon and comes back, their time will have passed slightly more slowly than the people on Earth. Therefore, they'll have gone into the future.
While we don't accelerate humans to near light speed, we do send them swinging around the planet at around 17,000 miles per hour aboard the International Space Station. Astronaut Scott Kelly was born after his twin brother and fellow astronaut Mark Kelly. Scott Kelly spent 520 days in orbit, while Mark logged 54 days in space. The difference in the speed at which they experienced time over the course of their lifetimes has actually widened the age gap between the two men. That's why astronaut Scott Kelly, that has spent a whole year at the International Space Station, aged slightly less over the course of a year in orbit than his twin brother who stayed here on Earth. So, whereas Scott used to be just 6 minutes older, now he is 6 minutes and 5 milliseconds older. The difference that low Earth orbit makes in an astronaut's lifespan may be negligible, better suited for jokes among siblings than actual life extension or visiting the distant future, but the dilation in time between people on Earth and GPS satellite flying through space does make a difference. The Global Positioning System, or GPS, helps us know exactly where we are by communicating with a network of few dozen satellites positioned in a high Earth orbit. The satellites circle the planet from 12,500 miles away, moving at 8,700 miles per hour. According to special relativity, the faster an object moves relative to another object, the slower that first object experiences time. For GPS satellites with atomic clocks, which are very precise clocks, this effect cuts 7 microseconds or 7 millionths of a second off each day. Let's make all that a bit more complicated and add gravity. According to general relativity, clocks closer to the center of a large gravitational mass like Earth tick more slowly than those farther away. So, because the GPS satellites are much farther from the center of Earth compared to clocks on the surface, that adds another 45 microseconds onto the GPS satellite clocks each day. Combined with the negative 7 microseconds from the special relativity calculation, the net result is an added 38 microseconds. That means that an atomic clock on board don't tick over to the next day until they have run 38 microseconds longer than the comparable clocks on Earth. Given those numbers, it would take more than 7 years for the atomic clock in a GPS satellite to unsync itself from the Earth clock by more than a blink of an eye. So, to answer the final question, can you time travel? Well, yes, you can, but today's technology will not get us anywhere near to the kind of time travel that we see on movies. With that said, we never know when there is going to be a scientific breakthrough that may let us actually travel to a significant amount of time. I hope you enjoyed the video. If you did, please leave a like and subscribe to my channel so you don't miss any upcoming videos.